Hello everyone and welcome back to a brand new video, and in this video I'll be solving problem connect all cities from Codechef starter 66. So let's move on to the solution. But before we move on to the solution, I want to tell you guys about Newton School's coding contest. So Newton School organizes coding contest every month. You guys can solve some quality problems and also compete against top coders in the world. This will be a good opportunity to benchmark yourself where you guys are lying in respect to other students in India or around the world. Not only that, along with this, you can also win some cash prizes. You can win rewards up to rupees 90,000. You can also win scholarships up to rupees 20,000. And along with this, there will also be some job opportunities. So this month, the contest will be on 30th of November. It will be around 2.5 hours from 9 p.m. to 11:30 p.m. So do not forget to sign up. The link will be in the description. So do go and sign up from there. So in the problem, we have been given an array A of size n, where n can be up to 10 to the power 5. So something like A1, A2, A3, so on up to an. All of these elements can be seen as nodes of a graph, right? So basically, we have n nodes. Now we want to make edge between these nodes, and we have been given an operation to do so. So we can make a edge of length L, or you can say a edge of weight L between two nodes I and j if AI and AJ and L is equal to L, right? So if the following condition holds, then we can add a edge of weight L between nodes I and j. And in the end, we have to answer if it is possible to connect all nodes. So we have to answer if it's possible to connect all nodes. And if the answer is yes, we have to find the minimum edge weight required to do so. And if the answer is no, we just print -1, right? So that is the problem. So given this operation, find if it's possible to connect all nodes, and if the answer is yes, find the minimum edge weight that is required to do so, otherwise print -1. So how can we solve this? So now let's move on to the observations. The one and only observation that we require to solve this problem is that every edge weight L will be a power of 2, or you can say the smallest bit common between AI and AJ. For example, let's say your AI is equal to 1001 and let's say your AJ is equal to 1101. Then if you find the AND of these two elements, we get AI and AJ is equal to 1001, right? So for now, AI and AJ and L has to be equal to L. We know the value of AI and AJ, it is 1001, and L has to be equal to L. So basically L has to be a submask. L has to be a submask of 1001, right? So there are only three possible values of L. These are 1001, 0001 or 1000, right? And obviously in the problem, we have been told to minimize the edge weight, right? So we will choose the minimum value among these three. So obviously we will choose the second value, that is 0001, and this is equal to 2 to the power 0, right? So every edge weight L will always be a singular bit, right? This is only a single bit, and it is the smallest bit that is common between AI and AJ. So if you see here between AI and AJ, this is the smallest bit that is common here. So in L, you will always choose this bit and set L equal to this common bit. So there are only 30 possible values of L, right? So for L, there are only 30 possible values, either 2 to the power 0, 2 to the power 1, 2 to the power 2, and so on up to to the power 30, right? So L can only be these 30 or 31 values. So now how do we solve the problem? So let me take an example and walk you through how we can use this observation or this fact to solve the problem, right? So let's say your array A is something like 1, 3, 4, 7, 8, 9, 11, 12, 13 and 15, right? So we have these elements. So first of all, I will write the binary form of all these elements. So binary of 1 is 1, binary of 3 is 11, the binary of 4 is 100, for 7 is 111, for 8 is 1000, for 9 it is 1001, for 11 it is 1011, for it is 1100, here it is 1, right, and here it is 4 ones, right? So now we know the binary form of all the elements. And as we know, there are only 31 possible values of L. And as we want to minimize the edge weight, and how do I achieve this? So to achieve this, first of all, I will try to make as many edges with weight 2 to the power 0 as I can. Then I will move to 2 to the power 1, then 2 to the power 2, so on up to 2 to the power 30. So if I want to make edges with weight 2 to the power 0, I have to find the numbers that have the 0th bit as set, right? So to make edges with weight 2 to the power 0, I will first find numbers that have 0th bit set, right? Because as we saw in observation 1, if you want to make a weight of edge L, then all the numbers should have that bit as set. So if I want to make edges with weight 2 to the power 0, then I have to find the numbers that have 0th bit set. So if we find these numbers here, we have 1, we have 7, we also have 3, we have 9 as well, we have 11, we have 13, and we have 15. So all these numbers have the 0th bit set. So I can add edges between all these nodes, right? So I can connect all these. And I will, weight here is 1, weight here is also 1, weight here is also 1. So it took me 6 edges of weight 1. So the total weight here is 6. So now I have made all the possible edges that I could have of weight 1. And to make these edges, I can keep a DSU, right? So basically DSU is used to store connections between components. So I can make a DSU and store these connections in a DSU, right? Then let's move on to 2 to the power 1. So now I have to make edges between elements whose first bit is set, right? So then I will find the numbers. I will find numbers whose first bit is set. For example, in this problem, we have 3, we have 7, and we have 11, and we have 15. We have 3, 7, and 11, and 15, yeah. But if we check here, if we try to make an edge between 3 and 7, it is not correct, right? Because 3 and 7 are already connected in a single component in my DSU, right? So before making an edge, before I make an edge, I will query my DSU. I will query my DSU and ask if 3 and 7 are already connected. And the answer is yes, right? Because in the previous step, we made an edge between 3 and 7. So 3 and 7 are in the same component. So I will not make this edge. I will just ignore this. Similarly, for 7 and 11, if I query my DSU, it will tell me, yeah, 7 and 11 are in a same component. So I don't have to make this edge. And same thing can be said for 11 and 15. So if I try to connect 11 and 15, I will query my DSU and check if 11 and 15 are in the same component. And the answer is yes, they are in the same component. So I will also not make an edge here, right? So I will make no edges for the first bit in this case. Then similarly, I will move on to numbers, find numbers whose second bit is set. So these numbers are, we have 4, we have 7. So we have 4, we have 7. We also have let's say 12, 13 and 15, right? We also have 12, 13 and 15, right? So first of all, let's think about 4 and 7. I will query my DSU and check if 4 and 7 are in a same component. But if we see here, there is no edge between 4 and 7. So I have to make an edge between 4 and 7. So I will tell my DSU, make a edge between 4 and 7 whose weight is 2 to the power 2. So I can also show that here. So I will make a edge between 4 and 7 whose weight is 4. Similarly, I will come to 7 and 12. Is there an edge between 7 and 12, or are they in the same component? And the answer is no, right? They are not in the same component. So again, I will make an edge between 7 and 12 of weight 2 to the power 2. So I can also show that here. So there is an edge between 7 and 12 now, right? Whose weight is 4. Then again, I will check between 12 and 13. Is there is some edge, or are 12 and 13 in the same component? So if you see here, now my 12 and now my 13 are in the same component, right? Because when I joined 12 with 7, 7 was in the same component as 13, right? So now my 12 and 13 are also in the same component. So I don't need to make this edge. Similarly, if I check for 13 and 15, they are already in the same component. So I don't need to make an edge here also, right? So I made 2 edges here. So in total, I made 2 to the power 2 into 2. That is 4 into 2, 8 weight, right? So I made edges worth weight 8 here, and previously I had made up to 6, right? Now let's move on to the third bit. Find numbers whose third bit is set. And these are 8, 9, 8, 9, 11, 12, 13, 15. 8, 9, 11, 12, 13 and 15, right? So let's check if 8 and 9 are in the same component. Are they? No, 8 and 9 are not in the same component. So I will make an edge between 8 and 9 whose value is 2 to the power 3. So I can also show that here. So I can create an edge here with 8 whose value is 8, right? Then if we check between 9 and 11, so there is an edge between 9 and 11, right? So I can ignore this. Similarly for 11 and 12, 11 and 12 are in the same component as well. Here is 12, here is 11, so they are in the same component as well. So I can also ignore this. Similarly for 12 and 13, they are also in the same component. And similarly for 13, 15, I can also ignore this, right? So I made a new edge here of weight 2 to the power 3. So 2 to the power 3 into 1, this is 8, right? So I think all my nodes are now connected, or you can say all of my nodes are in the same component, right? So now all of my nodes are in one singular component, or you can say all of them are connected. And it took me 6 plus 8 and then 8 again. So in total it took me 22 weight to connect all the nodes, or you can say make them into a single component. So that is the answer, and that is how you will solve this problem. And if you guys want to see the code for this, before I will do a brief summary also. So let me summarize the code or the solution. So your weights will only be in the set 2 to the power 0, 2 to the power 1, 2 to the power 2 up to 2 to the power 30. So you only need to worry about these 31 possible weights. And to do this, we will iterate from 2 to the power 0, or you can say from 0th bit, iterate I from 0th bit to the 31st bit, or you can say 30th bit, right? And in every step, find numbers that have the ith bit set, right? Let's say you store it in some set, let's call it, let's say array, right? So you find all the numbers that have the ith bit set, and you save them in an array that has some size m, right? So then you can start iterating from I equal to 1 up to m. If array of I and array of I plus 1 are in same component, or you can say they do have a component that they lie in, right? If they are in the same component, then you can just ignore, right? So you can query your DSU to check if they are in the same component. If they are, then just ignore. Otherwise, add them into the same component using DSU, or you can say make a edge between these two numbers, or you can say make a edge between these two numbers using DSU. And in your answer, you can add 2 to the power I, right? Because it will take 2 to the power I weight to add or make a edge between these two numbers, and that is the entire solution. So if you guys want to see the code for this, here is the code. So I'll start by taking my array of vector A as an input. Then I will declare a DSU. DSU will basically store all the components and nodes. Then I will make a vector of vectors, which is arr. This array of I will store the numbers which has the ith bit set. So I will go over all the elements from 0 to n, and then go over all the bits from J0 to up to J30. And if my element AI has the jth bit set, then I will push that element or its index into my array of J. Then I will start with allocating else. So I'll start from 2 to the power 0, go up to 2 to the power 29. So here J is equal to 0 up to J30. Then I will iterate over all the elements that are in array of J. And then I will start comparing adjacent elements to check if I want to make an edge between these two elements or not, right? So if DSU dot join array of Ji, comma array of Gi plus 1, I will check if these components are these nodes are in the same component or not. If these nodes are in the same component, DSU dot join will give me false. In that case, I will do nothing as they are already in the same component. Otherwise, I will make an edge of weight 2 to the power j between these two nodes, and I will add this to my answer. And in the end, I will check if all of my n elements are forming a single component or not. That is, if all of them are connected or not. If they are not, the answer is -1. Otherwise, I will just print my answer. So that is the entire solution. And if you guys have some doubts, feel free to join my Discord server. I'll be more than happy to answer your doubts there. And I will see you guys in the next one. Bye-bye.